Okay, good morning. So let's start. And today, I'm going to continue basically to finalize my story of modern cosmology. And yesterday, we discussed the basic picture of classical Big Bang cosmology. And as I was trying to show, in the last part of yesterday's lecture, we have kind of very nice playground there to study our, for example, particle physics models or something else. And also, we have to use many different areas of physics, and that's nice. And in principle, we can even, make predictions. For example, as I also mentioned, the primordial fluctuations of Newtonian potentials, they finally can be seen, like the temperature fluctuations of the cosmic microwave background. And okay, we do not have precisely the idea of initial conditions if we go for just classical Big Bang cosmology. But if we assume something very simple, that all the fluctuations are basically the same at all the scales, that's what is called Harrison-Zaidovich spectrum. Then we can predict the CMB fluctuations, and the result would be not so bad. It would not be precisely how we see it, but it would be quite similar. Are there some problems? Of course, and as always, when we are doing some kind of science, you might have some small problems with data, with experiments. For example, for primordial nuclear synthesis, when they predict the mass fraction of different nuclei in the universe, there is some tensions for lithium-7 prediction, for example. Not so big, but still more or less annoying, and some people are even brave enough to try to solve that by changing some kind of nuclear physics. And these kind of things. Also, when I say that we can predict CMB, cosmic microwave background, we can also predict large-scale structure in the universe. And but what Amr was too lazy to talk about, if you try to go for smaller scales, you do get some kind of small-scale structure problems in the usual cosmology. I mean, in the sense that when you do this, calculations, you usually get some kind of Caspi profiles of density of galaxies instead of cores, which are observed, things like that. But in principle, that's kind of very, very much non-linear regime, in which you might hope that maybe we are just doing some unjustified approximations for predicting that. And only in recent years they're trying to do some real numerical relativity simulations for these things. But as long as we are going for something which works in linear regime, in which you understand quite a lot, as long as we are doing that, the predictions are alright. So somehow it works well. Of course, there are some other problems, okay, nowadays we also have these troubles of H0 tension, the Hubble constant which we see from supernova measurements and can predict from CMB observations. Yes, there are some tensions which are really interesting now, and which make many people try some modified gravity or some other approaches which would be able to solve the problem. On the other hand, that's kind of some real life in science. You have some troubles, you try to solve them. Sometimes finally you find out it was just some systematic errors and nothing else. So something which also often happens in particle physics nowadays. So might be that's something interesting. Might be just some systematics in us to do next talk. I don't know. On the other hand, yes, we have some other problems like what I mentioned yesterday. We do not know why we exist at all, in the sense that why the baryons are much more numerous than antibaryons finally. And as I also told you, there are some conditions which we need to satisfy if we want to explain why there was violation of baryon-antibaryon symmetry. And standard model of particle physics, it kind of has all the necessary ingredients, but apparently not strongly enough. So there are some questions how we can go. That's also something interesting because we can try to solve that using some extensions of particle physics beyond the standard model, like grand unified theories and things like that. And yet one more thing is that we do have this dark matter. And dark matter, we know like since like 1930s, I think. Because we can just see that rotation of stars and galaxies goes kind of faster than it should be if it's just a visible matter. So somehow you have much more attraction to the galaxy center, and that's what is usually explained by dark matter. Okay, there are also some other problems, some other approaches, like people trying to modify gravity to explain dark matter. But that's actually not so simple, because all these stories like Mond, they're usually running into troubles. And also, you know, we also can see dark matter from other things, not only from rotation curves. You can also look at the gravitational lensing, and it also shows like extra matter content there. And actually, also like yesterday, I was showing like this acoustic wave equation for the primordial plasma. You can also study that. Instead of, you know, this Lindonian potential, you can translate that into the language of the density contrast in the primordial plasma. And you can try to see how the density contrast grows in your fluctuations. And if you go for like radiation-dominated universe, you can find out that the density contrast, it does not really grow quite well. It grows a bit, but quite slowly. If you go for matter domination, yes, you do have the density contrast growing. And that's also very important because dark matter is then a very important ingredient of how the structure of our universe was forming. If you don't take dark matter, usually you will have troubles to produce the necessary amount of structure. Okay, like in theories like Mond, for example, you might produce even more than you need, but you also have others. So the dark matter problem is that we still have not discovered it. Nowhere else from astronomy, only by gravitational interaction. And that's like also some other question to, let's say, particle physics, because indeed if you go for some kind of other things like grand unified theories or supersymmetric extensions, you do have some new particles there. And you might try to find here the candidate for dark matter. I mean, there was some excitement quite some years ago because, like for example, in particle physics, you have the problem of the mass of the Higgs boson, because it's a scalar particle, and usually radiative corrections are not stable, so that it's kind of hard to understand why the mass of the Higgs boson is so small and doesn't go very large due to radiative corrections. And one of the ideas was that supersymmetry might solve that. And like, you know, many people were playing supersymmetry games and very natural mass scale would be like around some tera-electron volt superpartners. And by some coincidence, people from cosmology also played some kind of games trying to see what kind of mass is natural to naturally predict the required amount of dark matter in the universe. And it was also around this particular mass range. So that was some kind of interesting coincidence, and that made many people happy, playing this with the interacting massive particles like for dark matter. But now we know that LHC did not find anything like that, and these simply supersymmetric ideas apparently don't work. So there is something interesting how it goes in history of science. But yes, for example, yesterday I also mentioned that, like, you know, if you look at the standard model, you can also try to find out if some non-perturbative effects might help you. And one of the things is that, yes, non-perturbative effects, they produce you baryon number violation. Okay, very small, but at least the idea. But on the other hand, non-perturbative effects can also bring some problems for you. Like, for example, in quantum chromodynamics, there is a strong CP problem. Like, because it seems that the non-perturbative effects should produce very large CP violation, which is contradicting all the experiments. In case we believe this non-perturbative quantum field theory approaches. But suppose you do believe, and then yes, there is this kind of strong CP violation problem in QCD. which people were trying to solve by introducing some pseudoscalar particles called axions. And then later, this kind of axions appeared like in huge amounts in string theories, for example. And nowadays, since we are no longer happy about wings, many of us are playing games about some very light axion-like particles called dark matter. And they might be very light, but still surface dark matter because of going to some Bose-Einstein condensate. So that's about dark matter. Another problem which we have, which we don't understand quite well, is dark energy. What is dark energy? Dark energy, and now I'm going to talk a little bit about dark energy because it also will be good for me for introducing inflation 5-10 minutes later. Dark energy means that what we have discovered, some 25 years ago, is that the universe is expanding, not decelerating, but accelerating. And that's something which, I would not say nobody could have expected, but that's kind of something unusual, because what you need for that, if you look at the Friedman equations, which I now write in the physical time, the Friedman equations, by physical time I mean like t squared minus a squared of t, the Euclidean element. If you look at this, and then, okay, your Hubble constant is a dot over a, and if I calculate h dot, then what I do I have like a double dot over a minus h squared, if I differentiate the denominator here, which means that a double dot over a is equal to h dot plus h squared. And if I want that the a double dot is less than 0, which means that the universe expansion decelerates, right? Oh, sorry, I want acceleration, so I won't have accelerates, then what it means? It means that h dot must be larger than minus h squared, right? That's kind of simple. And if I look here at the left-hand side, then I see that that is 2h squared, h dot plus 3h squared must be larger than h squared, right? Larger than h squared, which means that 1 minus 8pge, this guy should be larger than 1/3 8pg rho here, right? Which means that if I divide by minus 8 pi g, and dividing the inequality, I have to change the sign, I get like that the pressure must be negative and must be less than minus 1/3. So that's what I need. If I want to explain why the universe expands accelerated, then I need negative pressure, quite negative pressure. Okay? So one of the simplest ideas would be to take like pressure is equal to minus rho, that's the cosmological constant equation of state, and then that would mean that this guy is just equal to that guy, so 3h squared are equal to each other, which means that h dot is equal to 0. So the cosmological constant produces the theta-like solution of exponential expansion. Okay. So if I want to produce anything like that, I must go to something which is close to this, like cosmological constant. And that's kind of unusual to have negative pressure. So how can it be done? I mean, for example, yes, there is also one more question about the cosmological constant. The cosmological constant might have been like some just vacuum energy. But then you remember from lectures of Ade that yes, you have for every point in space-time you have this 1/2 of the zero energy of an oscillator, and basically you do get infinite vacuum energy. You just subtract that. And but indeed, like in usual physics, you only need the differences of energy. because like the difference of energy gives you the force, and then that's what you observe. But in GR you have this Einstein tensor equal to 8 pi g energy momentum tensor. And you cannot just subtract something saying I'm not interested. It influences your Einstein tensor. So somehow, okay, another idea is that, okay, maybe you could say that just if 1/2 doesn't have any meaning there, you have to remove that. But then, you know, also like in quantum physics, you have things like Casimir effect and stuff like that. So somehow, you know, this vacua are not totally no meaning. You know? So that's kind of hard. And the basic idea was that probably this quantum field theory works only until the Planck length scales. And then if you assume that you have one point only for at each like Planck length distance, then you don't have infinity. But basically then you predict Planck energy density scale for cosmological constant, which some 120 orders of magnitude away from what we observe. So that's kind of bad. And in principle, yes, some people can try to play with the supersymmetry, because supersymmetry indeed makes the vacuum energy density 0. But our model, our world is not supersymmetric for sure. And the supersymmetry must be broken, like, you know, at least like to the energies of LHC, or maybe even higher. So if you break down the supersymmetry at this kind of energies, you still have mismatch of like 60 orders of magnitude, which is like, you know, not much better. So basically you would need supersymmetry to the mass scales of like neutrino masses to reduce our observed cosmological constant, dark energy value. So that's something like, you know, some big puzzle for people thinking about quantum field theory and gravity and everything. And actually sometimes, yes, when I did not have dark energy, the idea was that, okay, maybe some principle makes the cosmological constant equal 0. Nobody knows what kind of principle, but that's kind of psychologically easier to believe. But now once we have, you know, some kind of particular value which is still not 0, that's much more difficult. Okay, but okay, let's now forget about cosmological constant. Let's assume that cosmological constant somehow is equal to 0. How could I produce the accelerated expansion still without that? Let's think about the simplest particle. I can think of some scalar. If I think about the scalar, like Lagrangian like that, then the energy momentum tensor can be found like very, very easily, basically like d mu phi minus g mu nu always Lagrangian. And basically, yes. And then let's assume that the spatial derivatives are not equal to 0. I'm thinking about cosmology, so I want to think of homogeneous state. So basically, all my derivatives here are only time derivatives. Then what do I have? Like here I have pressure. Then pressure density of my field is basically then kinetic energy minus potential energy. That's the pressure, which is here. And then the energy density I can calculate like, you know, like 0, 0 component. Then somehow here I have like phi dot squared. Here I subtract 1/2 phi dot squared. I get just 1/2 phi dot squared. And minus multiplied by minus, it gives me plus potential energy. So that's what kind of right hand side I get from the scaling. I have the energy density, which is the sum of kinetic energy and potential energy, and the pressure, which is the difference of kinetic energy and potential energy. Okay? So, what do I have here? Obviously, if I manage to have potential energy without kinetic energy, it means that I have negative pressure. I mean, it makes sense because like negative pressure, you usually think of some instability, and then if you have some big energy, the system would tend, you know, to develop some velocity to go down the potential. So that's the result. And then the question is, can I naturally make a scalar field have potential energy larger than the kinetic energy? Okay, one possibility is that you could just have potential like that, some false minimum here. And then, yes, you have some potential energy, and you don't have kinetic energy. And basically, this guy, if this thing you assume like no cosmological constant, then here you have more energy, and that's basically some non-zero cosmological constant. On the other hand, if you have some kind of very flat potential, you can have some kind of situation in which the field rolls like slowly. And then if it rolls slowly, its kinetic energy might well be less than potential energy. Yeah, so that's the idea. And even moreover, like in an expanding universe, it's even much easier to make it roll slowly. Why? Because if you look at the equation of motion, yeah, Gordon equation of motion, instead of V prime, I could put here like m squared phi, or just mass term, but I can also put some nonlinear potential, whatever potential I like. And then what I need to do, I need to calculate the inversion of the scalar field in this kind of geometry, right? But that's basically the divergence of some vector. And as I also showed you in one of the last lectures, it can be calculated like that. What is square root of minus g? I have here like 1, a squared, a squared, a squared. So the square root of minus g is a cubed. And either I just differentiate the phi dot and get phi double dot, or I differentiate a cube, I get like 3a squared a dot, divide by a cube, so I get like 3h. So basically this guy gives me like phi double dot plus 3h phi dot. Okay? And okay, also you can write like minus 1 over a squared Laplacian phi. But I assume that now I have homogeneous solution, so I forget about Laplacian. So that's the thing I have. And then my equation of motion goes like phi double dot plus 3h phi dot plus v prime of phi equal to 0. So how does it look like? It looks like having some kind of, viscous friction here. So this inverse expansion also add this kind of friction term to the equation, which means that it's even like, more natural to have slow roll situation than if it was just in some Minkowski space-time. So that's kind of good for us. So in principle, yes, if the effective mass here is smaller than this kind of friction coefficient here, then finally it goes to some slow rolling regime. Like if you have some kind of parachute falling down in atmosphere, finally the friction from the air makes the parachute going down uniformly, like uniform speed. So basically you easily get to have some kind of slow roll regime in which the velocity is like minus v prime over 3h. If you assume that acceleration is small already, you approach like the constant velocity regime, then basically the velocity to which you tend is this kind of velocity. Okay? So that's how you might try to construct dark energy. Okay, so that's basically what we have there. But even before dark energy was discovered, many people already were not very happy about how the cosmology works. And why? I mean, if I forget now for dark energy is just very recent. It gets the domination only now. By now I mean like last billion of years. Mostly all the universe expansion was decelerated. Basically like the scale factor going proportional to some power of t, the power less than 1. Like for radiation domination it's 1/2, for matter domination it's like 2/3, it's less than 1. And then, basically, if you look at the curvature scale, as I told also yesterday, A dot over A, it goes, of course, proportional to 1 over t, because the A derivative has one power less, which means that the curvature scale, like h minus 1, goes proportional to t. And that's also how you look at the what we call particle horizon. Like how far any signal could have traveled from the birth of the universe until now. It's proportional to the time until now, because that's like some constant lifespan. Then, if you look at the 1100 redshift, that's the time of recombination. That's the time when the cosmic microwave background was born. Basically, how big the particle horizon was there? Let's say instead of t, I put here t, but it's just the same as t because I put light speed to 1. So then it means like 1 over h, more or less, like with some coefficient I don't care now, with h at the time of recombination. Okay? And I mean, between recombination and now, let's forget about that energy. We had basically meta-domination epoch, which means that the scale factor goes like t to power 2/3. Then what does it mean? It means that the h is like 2/3 over t 1/3. I mean a dot over a. Huh? Oops, sorry, yes, over t. Over t. Which means like, let's say, proportional to a power 3/2. And since the temperature changes like 1 over a, or let's say redshift shows me like how much different the size of the universe was, it means that at the recombination h was square root of z times, or not square root, 3/2 power of z smaller than now, larger than now. So at the recombination it was z to power 3/2 h naught now. Yeah. Okay. The universe was 1100 times smaller at that time. It means that the h was 1100 to power 3/2 times larger than now. The expand accelerated. Okay. So basically, the particle horizon, how far any signal could have traveled before recombination, is proportional like to 1 over 1100 to power 3/2 h naught. H naught is Hubble constant right now. And when we look at this d, we see that at a distance which is like about 1 over h naught now, because that's like the farther thing you can see now is the combination. It's almost like from the birth of the universe, because it was, I don't know, like 100,000 years after Big Bang, and now it's like 13 billion years after Big Bang. So that's almost the same. And now you ask yourself, at what kind of angle you can see this thing if you look from that distance. Yeah. And here you might remember from lectures of Armor that it's not, this angular diameter distance is not precisely very similar to usual Euclidean, because like usually the angle will just estimate, like I take the size of the thing and I divide by the distance to this thing, and then I get the angle, right? That's the usual idea of angles in Euclidean geometry. Here it's not precisely like that. Why? Because, okay, the photons were radiated away when, this distance was also smaller by number z, by redshift, yeah? Which means that I have to multiply here by z, and then after that I will have the correct angle at which I see that. Yeah? Because, at the moment of at the moment of radiation, that was like, this d for that time, but the distance to us was, of course, d divided by z. Okay, more correctly, divided by z plus 1. Because the whole universe was smaller. And since then, the universe expands as a whole without changing the angles. Yeah? That's why the angular diameter distances, they must be corrected by these factors of like z plus 1. But anyway, basically what do we have from here? We have from here, like, in the numerator, we have 1 over z plus 1 to power 3 half h naught. In the numerator, we have like 1 over h naught. And we multiply the whole guy by z plus 1. We still have 1 over square root of z plus 1, which is like 1 over square root of 1100, which is about like 1 over 33. That's the angle in radians. And that would be something like 1.7 degrees, something like that. So basically, when now we look at the microwave background, if we look at 2 points farther away than just 1.5 degree from each other, we look at the points which could not have exchanged any information, any signal between each other since the birth of the universe. So like many hundreds of just causally disconnected regions are there. And still, when we look there, we see that the fluctuations of temperature are about 10 to minus 5. And that was a big problem which made people think like, how could have been like that? It's very unnatural. You had like, hundreds of causally disconnected regions, and somehow, without having any connection with each other, they produce the radiation which has almost the same temperature everywhere, like to the 1,000 of 1%, 1,000 part of 1%. So that's strange. That was the problem which made people invent inflation. What is inflation? Inflation is basically the idea that similar to dark energy, maybe like when the universe was very young, it did have some accelerated expansion. And if why did we have this problem? Just because the expansion was decelerated. If I look back and I want to see how much could they have exchanged information before radiating the CMB, not that much. Why? Because in the past the universe was expanding even faster than now. So the more I look back to the past, the expansion was faster. So that's why I get this problem that none of those separate regions could have exchanged any information, just because the expansion back then was faster than now. So if I substitute some period of accelerated expansion, then of course they would have had some chance to exchange information. Or more precisely, basically all of them initially go from almost the same point. It's just that the accelerated expansion just removed them far from each other. But before that, they did have some causal contact. So that's the idea. So you have to substitute some period of accelerated expansion before the classical Big Bang phase, and then you get your result. But in principle, there was some connection. You can ask yourself how much of that expansion you need. And that's usually presented in terms of E-folds. The idea is that we assume that inflation goes almost exponential. And basically, it expands like E to some number of times. And each expansion by E times, you call like E-fold. So if you have expanded this number of times, you say that you have n E-folds of inflation. And then, yes, I don't have time to show like the details of calculations, but you can check that if after inflation you assume that your universe comes to temperatures of around grand unified theories, a bit below grand unified theories, you will need like 50, 60 E-folds of inflation. Which basically means that the largest scales we observe now, they correspond, to the conditions of inflation before ended like 50, 60 volts before. Okay? Okay, in principle you can play games also here. If you want to exit inflation at Planck energies, you would need like 70 volts. If you're brave enough to finish inflation just before nuclear synthesis, then you will get like 20 volts maybe, but you would have other troubles. Okay, so that's the idea. And then people also found out that yes, you can use the scalar field. And initially there was the idea which was called old inflation, like good, that you did have some kind of false vacuum, and then by tunneling you go to some new bubble of our universe. And then after that, these bubbles, they merge with each other, and by merging they create temperature and then heat the universe, and you get Big Bang. Almost immediately people realized it didn't work like that. Why? Because when you are here, you're in the Sitter space, in a space which expands exponentially. Whatever 2 points you have, very soon they would be removing from each other faster than light, just because they're far away. And that means that if you have this kind of transitions here, then if the transition occurs rarely, then yes, your bubble here is just destined to be alone in a huge empty universe. So either you have all these transitions very often and then they can merge before they're taken far away, but then they don't have any inflation, it just goes immediately. If you have some time living here, then yes, your new bubbles, they cannot meet each other, so it doesn't work like that. But then after that, people introduce new inflation, which means which means that you have some part here, and then your field might roll slowly, and then yes, you have some period of inflation, because here you would have small kinetic energy, but relatively large potential energy, so you have inflation, and that's what was called new inflation. In principle, what is bad about it is that you need some fine-tuned initial conditions, because if you had some large velocity here, then your Hubble friction would not have time to stop your field before it just goes to the minimum. So you need to find to justify initial conditions with small enough velocity here, otherwise you just miss your option. Then Andrei Linde, he said, okay, but you can also go for just some mass term, for example, and rolling down from there. And if you roll down from large fields, then yes, you do have time to stop your large initial velocity, and then the field goes to some kind of slow roll regime here. And yes, that's what is called chaotic inflation. Chaotic because you don't need to fine-tune your initial data. Unfortunately, these chaotic models now they contradict observations, because in those models they usually predict too many gravitational waves, more than the restrictions from polarization measurements of the CME. What is maybe the most successful now are models like Starobinsky, which in scalar tensor representation they have the field with potential which goes like to some plateau for infinite values of the field. And here, since you have this plateau, you still don't have too much of gravitational waves, but you can have the initial data very far away from the minimum, so you can have time to stop your to break down your high speed of rolling, and then you have the slow roll regime here. Okay. So that's the basic ideas of inflation now. And now, okay, in the remaining like 20 minutes, I will now try to give you some idea of what you can do with that. Okay, first of all, let me tell you that you have to take care of your slow roll conditions. Indeed, the field rolls slowly, so that kinetic energy is much less than potential energy. And basically, there are two two standard definitions of parameters, which are called slow-roll parameters. One of them is epsilon, like first slow-roll parameter, 16 pg is v prime over v squared. That indeed potential is flat enough in a sense. Yes? And the second slow-roll parameter, which would be like 8 over 8 pg a double prime over v. Basically, this flatness is not violated very soon by the second derivative, right? And then, yes, you take this equation of motion, and your slow-roll approximation is that you assume that you can just neglect phi double dot. You say that phi dot is minus v prime over 3h. You assume that 3h squared is given just by the potential energy, so that you can neglect kinetic energy here. So you have these approximations, and then you calculate what you get. For example, like, for phi dot, you can calculate, you can substitute h like a square root of v, the coefficients here. And then what you can do, you can find out like what is phi squared over 2, phi dot squared over 2 over v. Like what is indeed the ratio of kinetic energy to potential energy. Yeah, so very simple. You do calculations, you get something like proportional to v prime squared, and then this h squared is proportional to v, and you have one more here, you have something proportional to v prime squared over v squared. So I don't spend time now for calculating it explicitly, but basically you get epsilon over 3. Like if you do all calculations accurately, you will have like this 48 pi g coefficient here. You can also try to check if indeed your solution is close to is close to the Scalar. For that you can calculate h dot over h squared. Okay. Just by taking h dot differentiating this equation, so basically h dot would be proportional to v prime phi dot, right? If you differentiate by time this. And then you substitute it here, also h squared is given by v squared. So basically again, v prime also has one more v prime, f dot has also one more v prime there. You get phi prime squared over h. And then you substitute everything here, and you can show that that's minus epsilon. And it shows you that the expansion is close to the theta if epsilon is small. Yeah, because this shows you how much h changes in a time frame of 1 over h, right? So that's basically the difference. And finally, if you do all these calculations, you might want to check if indeed you are correct about neglecting the acceleration here in this equation. How can you do that? You can estimate what would you get if you take f double prime and divide by h f prime, f dot, phi double dot over h I dot. How you do that? You just take this definition of f dot, differentiate it once more, substitute here, substitute f dot also here, and h in terms of v. And of course, because you also differentiate once more, you get f double prime, right? And then you can see that what you get is basically epsilon minus eta. Those slow parameters. So indeed, as long as not only epsilon but also eta is small, you're all right. You have kinetic energy much smaller than potential energy. You have expansion very close to the theta, and indeed it does not get violated like in time, because indeed you could have neglected the second derivative time derivative, say indeed small. Okay. So that's basically how it works, and then you can take whatever simple potential like m squared phi squared over 2, and you can see what does it mean to have it small. It means to have 1 over 5 small, basically, right? So basically you have to, for this kind of chaotic inflation models, you have to take phi larger than Planckian value, and then it goes down, and once it reaches Planckian value, the inflation stops because the slow parameter is no longer small. Okay? So that's the idea. Basically, this kind of 60 folds of inflation is not so difficult to get because you can check that you start from just several times larger than Planck mass, and then it's enough for giving you 60 folds of inflation. So basically, the idea is very simple. You can do that. Then, what else can you get from inflation? Yes, you see that it's kind of very simple. You have solved it. You found how to produce this accelerated expansion. Yes, I mean, if you don't care about observations, yes, just take the mass term, take it like several times larger than mass Planck, and then yes, while rolling down, yes, several times to the Planck mass here, it gives you like 60 folds of inflation. That's it. But what else can you get from that? Just okay, yes, you have solved the initial conditions because before inflation, then all your regions were causally connected with each other. Okay. Another thing you can solve is that you can solve the flatness problem. Like all our observations tell us that the universe is very well described by this simple metric. That the spatial section is Euclidean, is flat. It might have been some sphere, it might have been some hyperboloid, but somehow its curvature is so small that you don't see that. It's almost totally Euclidean. And that's kind of problematic. Why? Because if you look at the radiation, the density of radiation goes like 1/84. If you get matter, its density goes like 1/AQ. If you take curvature here, the contribution of spatial curvature would go like 1/A². And nowadays, it's less than 1%, the difference of density from critical density. Which means that, some time ago, it must have been extremely tiny, with no explanation why. So then, if you produce a universe like at some high temperatures, you must have produced that with absolutely tiny spatial curvature. And there is no idea why it should have been like that. Why it should have been almost precisely zero. So that's again something which inflation solves for you. Because if you had some accelerated huge expansion, and even if you had a ball, finally this ball would look almost like a plane. So that's, and again you can check that this kind of 60 folds of inflation also solve for this problem. Okay? And now the final point I want to make is that actually even more than that, inflation produces perturbations for you, from quantum perturbations of quantum fields. Why is that? Because during inflation, this curvature scale stays almost constant. Because the Hubble constant almost doesn't change, it's almost exponential. But the wavelengths, they grow like scale factor. So every wavelength was very small initially, then it grows, it becomes much larger than the curvature scale during inflation, and it stays like outside the horizon. It has its constant modes there, so we don't even need to know much physics to predict what it grows. And then after inflation, the universe goes to this rate expansion regime, and then those modes from outside horizon go inside horizon. They continue growing, but they grow slower than the curvature scale of the universe. So, and that means that all the waves we observe now, at some point before, they were very small, Planck scale. So there should have been some quantum fluctuations, which you can see now as perturbations of the universe. Yeah?
It's very obvious that inflation solves a lot of problems with our model, and it explains a lot of stuff.
Mm-hmm.
So do we have any idea as to why inflation would occur to begin with? Any insight?
That's a good point, yes. I mean, in principle, yes, people are trying to argue that, yes, if you have some kind of scalar field, then yes, it generically has some kind of initial conditions which asymptote to inflation. But then, yes, other people could say that it's wrong because for that you must assume that the spatial gradients were small. If they were kind of chaotic, then you don't get that. So that's another question, yes. But yes, if you believe that there might have been some bubble with small spatial gradients, then yes, you have very good chances to get some kind of exponential inflation after that. So, but then, yes, let me just very briefly tell you about quantum fluctuations from inflation. And for that, I will choose to predict gravitational waves. Unfortunately, we still have not seen them. I mean, from inflation, like B mode of polarization. We have seen only black hole emerges. But actually, so the idea is the following.
When are we going to observe them? When are we going to observe?
Depends on how much we have. If chaotic inflation of Andre Linde was correct, then already Bicep and Planck should have observed that. And since they did not, it means that his chaotic inflation is not correct. And you know, some 7 years ago, Bicep was announced, and they found this B mode of polarization, basically primarily gravitational waves, which appeared to be just some dust. Dust in direct meaning, dust in the universe. And Andre Linde was drinking champagne for that because his model was great. Finally, no, he was wrong. Okay, let me just very briefly tell you about how to predict that. So you remember we had this kind of equation, and now I go again to the yeah.
Like I heard about the experiment that talks about the gravitational waves at the microwave background, and it was ruled out by dust. But the thing is, I heard, I don't know if it's true, that they will do another experiment that use different wavelengths. The dust will affect the different wavelengths differently, but the inflation will not, and they will try to figure it out. But I don't know how long we went through this experiment.
I mean, in principle, there are several directions. Like one idea is that maybe we could, see primordial gravitational waves directly from things like LISA antenna. That's one thing. And another thing is that all these Bicep and Planck things, they also we could also probably try to build some new detectors, more sensitive, so that they could go for lower tensor to scalar ratios and perturbations to check. That would be for CMB. So for now it hasn't yet happened, but yeah, I mean there are some hopes, of course, and that might be an interesting point also for cosmological experiments, just because we still did not measure that, and I would say we're already basically exhausted what we can get from temperature fluctuations. So if somehow we could try to get the polarization signal, that would be great. Yeah. So that was the equation for gravitational waves, and you can actually try to check that. That basically means that the quadratic action for gravitational waves in expanding universe would be like that. And here we get our problem that the action gets time-dependent coefficients. That's very similar to what Shemet Das was mentioning in his first lecture. And that's actually also a problem of how do we quantize fields in a curved space-time. Because usually we quantize in Minkowski space-time, and then it's very simple, like you have these plane waves, and you have all the symmetries. And what is very important for quantum field theory is like separation to positive and negative frequency solutions and everything. So usually we don't have that here. And actually we even don't have the idea what kind of vacuum should be here. Like it's probability of transformations also mentioned by Shami. But still, what we usually do here is, okay, let's say I have this H. I try to transform the action into a simpler form. And here we have two polarizations. Let me just say, okay, I have one polarization plus another polarization. And let me just take one polarization. And for this polarization, let me take Hij, like square root of 32 pi g V over A, and then some polarization tensor like of unit norm, plus another. If I substitute that, let me just take only one polarization here, just 1, 3, and I get the action like that, 1/2, and here I have T for X. And basically, why did I do that? To produce, to turn this coefficient to the usual 1/2 and to kill a squared here. So I get basically like v dot squared minus dv squared. But I also had to differentiate a substituting here, and you can check that what you basically get, you get plus a double dot over a v squared. So basically you produce the model which is kind of scalar field in Minkowski space-time with time-dependent mass. So we want to quantize that. And others still didn't die?
No, it isn't. You can.
Okay, then I'll take a bit more time.
Yeah. You still have 5 minutes anyway. You started at 9:30?
Yes.
Okay, so you still have 5 minutes, then you can take another 5 minutes.
So basically then what we have, and what I didn't say, I have to work now in conformal time. And the de Sitter space-time in conformal time I can write like that. And my time goes between minus infinity and 0. 0 is infinite future, minus infinity is infinite past. I mean, if you try to go to physical time, then yes, the differential of the physical time should be like, you know, here, like that. And I take the scale factor as minus 1 over ht. Basically, yes, the differential of the physical time should be this a of t differential of the conformal time. Then dt over t is d of logarithm t, so that's why what I had like exponential in physical time, in conformal time I have it like that. And then basically what I get this mass, which goes, okay, basically let me go to Fourier mode. I take some kind of wave vector, and here I will get something like 2 over t squared for this mass, just differentiating this a. And then basically I will have equation like that: v double dot plus k squared minus 2 over tau t squared, v equal to 0. So instead of the usual harmonic oscillator, I will have some kind of time-dependent frequency here. And basically the idea now is as always, like I put like v, I put dk cube over 2 pi cube square root of 2k, and I get always minus ekx vk of t creation operator plus vk annihilation operator, so like the usual thing. I think Adri was putting here square roots, but I just have different convention for commutative creation annihilation operators. I put 2 pi cube here and then theta function. So anyway, you go like a usual quantization of fields, and then you want to calculate what kind of vacuum expectation value of v squared you have. That would produce for you like the natural level fluctuations. Yeah? For doing that, I would say let's take like vx, vy plus vy, vx with some separation to not have the squares. And then yes, and then you do the calculation what Adri was showing. Like if you have annihilation to the right, you get 0. You have creation to the left, you get 0. Otherwise, you just do the commutation of creation annihilation operators and you get the final answer. So then you can do this calculation. But the question now is what kind of solution I put here. Because in principle I can go for different solutions here. Like also Shamit was discussing about time-dependent frequency of the oscillator. And the basic idea in cosmology is that in principle, if I go to the infinite past, I have a wavelength which is much, much less than the curvature scale of the universe. It basically lives like in Minkowski space-time. So the idea, what is called Bunch-Davis vacuum, let's take like, the usual Minkowski Q of t at the time minus infinity times. And then you can see that this equation you can solve like Vk of tau equal to Ek tau 1 plus K tau. Okay, I say t instead of tau, so tau. Like that. So basically you start at minus infinity time, you start from some plane wave, and then it grows when t approaches 0. And you substitute it here, and you want to see to what it tends when t goes to 0. And 0, I remind you, is infinite future. Basically, then you also have to see that the module V tends to 1 over kt, of course. T, you can substitute like t is equal to a to 1 over ah from here, and you should also play some games with the three-dimensional integrals. So finally, let me just give you the result. It's not very difficult to do, but we need time for that. K is like, R is the module of x minus y, the distance at which you have it. So basically now you can send R to 0 to just reproduce the square of your field. And that basically means that for every logarithmic distance in the wave number scale, you get the typical square of the fluctuations, like h squared, a squared over 2 pi squared. Okay. And finally, if I want to produce the how much of the gravitational waves are produced, instead of v I have h, I multiply by the square root squared, I multiply by a squared to the denominator, which gives this a squared here, and I multiply by 2 because I have 2 polarizations. So I have it like that. And the final result, which is very easy to see here, but I'm afraid that I would make a mistake if I do it in mind. That would be like 16h squared over pi, let's say mass Planck squared. By mass Planck squared, I just mean this guy here. Okay? So that's the final result for the gravitational waves. And actually, what I was doing here, I was assuming that the universe is just de Sitter. So that's why h was a constant. In principle, like the real inflation, it has some change in time, Hubble constant. And basically, that what it means is that, different wavelength, they felt a bit different Hubble constant. What Hubble constant? I mean, basically, the idea is that you have to take the Hubble constant, which was there when the wavelength was exiting the horizon, because after that it stays constant. So basically, you have to take it at the horizon exit. And since the longer wavelength, they were in the younger universe there. Yeah, the longest ones, they exited the Hubble radius earlier. So then the longer wavelength, they did have a bit larger h, because h always goes down. It stays almost constant, but decays a bit. So you have some red tint. Red waves are a bit stronger than violet, let's say. Yeah. So longer wavelength have a bit larger amplitude. So unfortunately, this red tint by now we cannot check because we have not discovered the primordial gravitational waves. But what we have done for scalar fields, and yes, I'm taking like a few more minutes to just mention the scalar field. And in
Yeah, you
principle,
can get NS for the,
huh?
you can get NS for the scalar field. When you grant it.
Yes, yes.
Yes.
So you want to derive also the
Well, if you have a few minutes, maybe you show them NS and so on. Or, well, it's up to you, of course.
okay. I mean, actually, if to derive the spectral field, it will be much easier to derive for the gravitational waves because here I only have H. Basically,
Oh, yeah.
for the scalars, it would require.
It's a bit,
Yeah. But actually, I mean, I can just say at least to know the result that I want to find the scale for the spectral tilt, and by spectral tilt I mean just the double logarithmic derivative of the amplitude with respect to the wave number. Okay, and yes, I just have to see, you know, if I have different wave numbers, yeah, how much different was the time at which they were exiting the horizon, and then how much different was the Hubble constant for them. And basically, you can do calculations and you can check that that's minus 2 epsilon. Epsilon is the first slow parameter, and epsilon must be taken like some 50 e-folds before the end of inflation. Because if you are looking at the largest wavelength now, that's what was there like 50 e-folds before inflation stopped. So basically, you need to know v prime over v squared some 50 folds before inflation stops. So if you have some model of inflation, you definitely can find out what kind of v was there. And for the scalar fields, let me just say the following. In principle, what you want to predict this kind of thing R, which is like psi plus h beta phi over phi dot. Why you predict that? Because remember when I was discussing yesterday the scalar perturbations, the psi or phi, they were kind of changing if you change the equation of state parameter of the matter. What is kind of what has stable large wavelength modes is parameter psi, which I wrote like delta rho over 3 rho plus p. Or also at large scales you can write it almost as R, which is like psi plus h a plus h u over a, where u is the velocity potential of the ideal fluid. And basically that's it here. The variation of phi gives you a potential velocity because velocity is proportional to gradient of phi. So you have to predict this guy here. And basically, if you want to do it accurately, you need to find some kind of Mukhanov-Sasaki variable, which has action very similar to action for the gravitational waves, at least like in the Slow approximation. But actually, as long as the Slow approximation is correct, basically you should quantize delta phi itself. You should quantize the inflaton, which is very simple. It goes the same way as I did for gravitational waves. But then what you predict not precisely the fluctuations of delta phi, but then multiply by h over phi dot. H is the Hubble constant, phi dot is the velocity of the scalar field. And what you basically get, you get the delta r squared, this amplitude, you get h squared over 2 pi phi dot squared. So because I multiply by one more h, instead of h squared, I get h to the 4. And because I have to divide by phi dot, I get phi dot squared to the denominator. So I have this kind of prediction for the amplitude of scalar perturbations. And since Amor was asking about observational predictions, and I can also give you the results. You see, since here, not only h changes.
You need to wrap it up because Shomit wants to talk now. He has very special.
Okay, maybe 5 minutes.
But you can take some time tomorrow if you wish.
Yeah, that's possible, yeah.
Okay. So
Okay, can I just take 5 minutes?
A bit
Can
more
I take
time.
5 minutes right now and then?
Okay.
5 minutes.
Yeah, just because he has some very special.
Okay, I just want to know to finalize what I was saying. So basically you get like this, and then now if you want to find the spectral tilt, not only age but also find dot changes. That's why the result for this spectral tilt, and here we have some difference, in notations. They call it spectral tilt like -1, analogous double logarithmic derivative. And they get for that 2 eta minus 6 epsilon. In principle, here you might produce also kind of blue tilt, but usually for simple models you get also red tilt, like for gravitational waves. Why? Because when inflation goes, generically H goes down and phi dot increases, because the field just accelerates a bit down to the down potential. So you also get the red tilt usually, and also you can compare this amplitude to that amplitude, and that's what is called scalar to tensor ratio. For scalar to tensor ratio, which means I take the ratio from H to R, I get 16 epsilon. And you see, if I really want to say that my gravitational waves are very, very weak, I need that I have really slow or very, very slow. Epsilon must be really very, very small if I want to have much less gravitational waves than scalars. And that's what makes this scalar, the chaotic inflation problematic now, because it predicts like 0.16 for tensor to scalar ratios from mass to inflation, and now we know it's definitely less than 0.1. So that's why the chaotic inflation now is important. So yes, that's what I wanted to say now. So I produced all these basic predictions from inflation. Yeah, maybe tomorrow I could
If you want to continue,
give just a bit more detail and then discuss about modified graphics.
Yeah. Okay. Then you need tomorrow. Okay, but we keep it tomorrow at fairly like the more we try a discussion.
Yes.
Yeah. Okay. So any questions? You leave it till tomorrow. I'm sure you have a lot of questions. Sorry. So it's just.